We're going to talk about types of bonding, ionic versus covalent, and here are your learning objectives for this video. Pause the video and write them down. Let's take a look at how atoms connect to one another. We're going to be looking at two types of bonding. The first is called ionic bonding. The nature of ionic bonding depends in part on the elements involved. We're going to look at sodium, for example. Sodium has an electron configuration of neon 3s1. And that means that sodium has one valence electron, one dot. And we're also going to look at chlorine. And chlorine's electron configuration is neon 3s2, 3p5. The organization or arrangement of electrons in sodium's valence shell, 3s2 electrons like that, 3p. There are, of course, 3 atomic orbitals, 5 electrons, 1, 2, 3, 4, and 5. So chlorine gets 3 pairs and 1 unpaired electron. An ionic bond is going to be essentially just a transfer of electrons. Now sodium, we know, wants to be stable. It wants to be isoelectronic, or have the same number of electrons as neon. Neon, if you remember, is 1s2, 2s2, 2p6. That's neon. And neon is stable. It's a noble gas. It's stable because it has 8 valence electrons. Well, the rule that says that that has to be the case is called the Lewis octet rule. So the Lewis octet rule says that all elements want to have 8 valence electrons to be stable because the noble gases have 8, an octet of electrons. So sodium wants to get rid of its 3s1 electron. It really would like to get rid of that. This lone dot is keeping sodium from being stable. Chlorine, on the other hand, is very, very, very close to having a full valence shell. It has 7 valence electrons. It would very much like to be like argon. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. That is argon. That's the closest noble gas to chlorine, and chlorine would very much like to be it. Chlorine is missing 1 valence electron. So we can show what happens between these two elements if we simply allow sodium's 1 electron, its 3s1 electron, to be transferred over to chlorine. Sodium wants to get rid of 1 so that it will have 8. Chlorine wants to gain 1 so that it will have 8, like argon. And in doing that, in just allowing sodium to transfer 1 over, sodium becomes an ion, but now electronically stable. Chlorine becomes an ion, but also electronically stable with a minus charge. And because these two have opposite charges, they're going to attract each other to make sodium chloride. Sodium chloride, of course, we write as NaCl. Now we can do the same sort of thing with all kinds of different metals and nonmetals. For example, if I want to do calcium and nitrogen. So calcium has 2 valence electrons and they are paired. Now if you don't remember how to do that, you want to get yourself a periodic table, and you want to make sure that you know how to get the number of valence electrons by looking at where the element is. If you have the periodic table numbered with these Roman numerals, the valence electrons are very easy. Group 1 has 1, Group 2A has 2, Group 3A has 3, Group 4A has 4, and so on and so forth. The only thing is that this is labeled as Group 0. It's often labeled as Group 8A, and because they have 8, of course, except for helium. So calcium is in Group 2. It has 2. It is 4s2 is its valence shell. It's right after argon, 4s2, so it has 2, and they are paired, which is why I have a pair of dots here. Nitrogen has 5 valence electrons. They are arranged as a pair and 3 unpaired electrons. Again, nitrogen has 5, it's 2s2, 2p3. and the 3 electrons in the 2p sublevel have to be separate in separate orbitals because of Hund's rule. So we can show how calcium and nitrogen will bond. Well, calcium is wanting to get rid of these 2 electrons, so it can give 1 and 2 to nitrogen. And when it does that, it becomes stable. It becomes charged, yes, but stable. Its dots are now gone. Okay? So there you go. But this nitrogen is not yet stable. The nitrogen just gained 2 electrons, but it needs 1 more. It needs 1 more electron to be stable. Well, that means I'm going to need another calcium with its 2 valence electrons. And that calcium can give 1 of its valence electrons to this nitrogen just like that. And when it does that, nitrogen now is stable. Nitrogen has now 8 valence electrons, just like its nearest noble gas. It gained 3, so it has a -3 charge, but it's now stable. But this calcium still has 1 more electron that it needs to get rid of. So that means I need another nitrogen. I'm going to put in another nitrogen with its 5 valence electrons, and the calcium will give its 2nd electron to the nitrogen. And when it does that, the calcium now becomes a calcium ion, stable with a charge. But this nitrogen needs 2 more to become stable. It's not stable yet. So that means I need a 3rd calcium atom with its 2 valence electrons, because this calcium is going to want to give its electrons 1 and 2 to nitrogen. And when it does that, the calcium atom becomes a calcium ion. It is now stable, but with a charge. And the nitrogen now has gained its 3 that it was looking for, and it becomes stable with its 8 dots and its -3 charge. So now everybody's happy, everybody's stable. I have 3 calciums, and I have 2 nitrogens. And so the formula that I will write is Ca3N2. 3 calcium ions, 2 nitrogen ions. The metal is always written first. This is called calcium nitride. Let's take a look at hydrogen and chlorine. So hydrogen only has 1 electron, so it must have 1 dot. Chlorine we saw already a little bit earlier that chlorine has 7 dots, and they are arranged in 3 pairs and 1 unpaired. Now the question is, how come hydrogen doesn't just give its electron to chlorine, becoming an H plus and a Cl minus and forming an ionic compound? We know that H and Cl are both nonmetals, and therefore they don't form ionic compounds, they form covalent compounds. So how come sodium with its 1 dot can transfer an electron to chlorine and become sodium plus and Cl minus and attract each other and make a nice ionic compound, sodium chloride? Why doesn't hydrogen do the same thing? The answer boils down to something called electronegativity, which you remember means electron greediness. It turns out that the electronegativity of hydrogen, the greediness that hydrogen has for electrons, and the greediness that chlorine has for electrons are very close. As a matter of fact, if I look it up on a table of electronegativities, I will see that hydrogen here has 2.1 and chlorine has 3.0. So the electronegativities of the 2, hydrogen we said was 2.1 and 3.0. And depending on the periodic table that you use, you'll see different values for these 2. But ultimately what it means is that the greediness of hydrogen is very close to the greediness of chlorine. And because both atoms, hydrogen and chlorine, are greedy for electrons, hydrogen, if you remember, only needs 2 electrons to be stable. It needs to be like helium, and it's already got 1. It's very close to having its 2. It's very, very desperate to get 1 more electron. Chlorine needs 8 to be stable, like argon. Well, it already has 7. It's 1 away from having 8. So it's very desperate for electrons. The fact is, though, chlorine is not greedy enough to take hydrogen's only electron, and hydrogen isn't greedy enough to take 1 from chlorine. Their electronegativity difference is too close. It's too small. So the difference between these 2, 3.0 minus 2.1, is 0.9. That's the difference. 0.9 is less than 1.74. And so these 2, neither one is strong enough to steal an electron from the other. And so what they do instead is they share a pair of electrons. This pair of electrons right here. Hydrogen wants to fill up the empty space in its 1s orbital. Chlorine wants to fill up the empty space in its 3p orbital. And so if they share the two electrons together, they each get to count this shared pair of electrons as their own. And so now chlorine gets 1, 2, 3, 4, 5, 6, 7, 8. Chlorine now has 8 valence electrons, which makes it stable. Hydrogen has 1, 2, which makes it stable. So by sharing a pair of electrons, we form something called a single covalent bond. And usually we represent that as a line between the two elements that are bonded. So there is my shared pair of electrons. So the line represents a pair, 2 electrons. These other pairs around chlorine here are not participating in bonding, but they are important. They're called lone pairs. And they are important when I'm showing the bonding in a molecule, but they are not involved in bonding. So lone pairs is what we usually call those. The pair of electrons that's shared is called a bond pair, or just a single covalent bond, or just a bond. The last thing we'll talk about is the nature of the bonds themselves. So we will see things, for example, like fluorine. Fluorine, 7 valence electrons, just like chlorine, it's in chlorine's family. And when fluorine is by itself, we know fluorine doesn't like to be by itself because fluorine is so desperate for one more electron. Fluorine has the highest electronegativity on the periodic table, 4.0. Some places it says 3.9, but 4.0 usually. Fluorine, when it's just around itself, just around other fluorine atoms, in order to become stable, fluorine can share a pair of electrons with another fluorine atom. Now, obviously, the difference in electronegativity between two elements that are exactly the same, the difference is 0, which is much less than 1.74. And so we have fluorine with a single bond in between two fluorine atoms. Well, we already knew that fluorine is a diatomic. It's F2, and the reason it's F2 is because it needs to be stable. And we see that with all of the other diatomic elements. So F2, Cl2 will do the same thing. Like that, forming Cl2, the diatomic molecule. These are now called molecules. They're not atoms anymore. So there's Cl2. I2 does the same thing. Br2 does the same thing. H2 does the same thing because hydrogen only has the 1 valence electron to work with, and so it can share that pair of electrons to make H2. So these are 5 of the 7 diatomics right here, showing that they are diatomic because they need to become stable. Well, what about oxygen and nitrogen? Similar. Oxygen has 6 valence electrons, 2 pairs and 2 unpaired electrons. You should be able to draw that by now. And if there are other oxygen atoms around, then oxygen, in order to become stable, each oxygen needs 2 electrons more to become stable. They have 6, they want 8. Well, if you're just around other oxygen atoms, neither oxygen is strong enough to pull electrons away from somebody else, so they just instead share 2 pairs of electrons. And when we share 2 pairs of electrons, we get something called a double covalent bond. 2 shared pairs is equal to a double covalent bond. And when we're drawing it, we would draw 2 lines between the 2 oxygens. And don't forget the lone pairs. And the same thing we could have with nitrogen, where nitrogen has 5 valence electrons, 1 pair and 3 unpaired electrons. Each nitrogen wants to gain 3 more, but if it's around other nitrogen atoms, it's not going to be able to gain anything from the nitrogen atoms, so instead it can share 1, 2, 3 pairs of electrons. So we have 3 shared pairs here. and we call that then a triple covalent bond, which we can represent by 3 lines. So that's all 7 diatomics. Now, there are no such thing as quadruple covalent bonds. They don't exist. Last thing we'll talk about then is something called bond strength, which how strong a bond is, how much energy it would take to break it. That's bond strength. And for bond strength, the general idea is that single bonds are weaker than double bonds, which are weaker than triple bonds. So it takes more energy to break a triple bond than it does to break a single bond, and this double bond is right in the middle. Conversely, we can look at how long the bonds are. We call that bond length. And in bond length, the triple bonds are the shortest, and the single bonds are the longest. So single bonds are the weakest but the longest bonds. Triple bonds are the strongest but the shortest bonds. So we have 2 different types of bonding. Ionic bonding, we transfer electrons. Covalent bonding, we share pairs of electrons. And in the next lecture, we're going to learn how to draw covalent molecules.